The main drawback of the Holy model is that it allows negative interest rate. Actually, nowadays, negative interest rate indeed happens. So we can regard actually this as the advantage of Holy model. But anyway, Holy model does not allow negative interest rate. Some people don't like it. They want interest rate always positive. So as an alternative of Holy model or slight modification of Holy model, we have BDT model. And BDT model basically models the exponential of interest rate, some exponential value. Therefore, it is always positive. So in other words, we take log of interest rate, and then we model z, process of z, zij, which is log of rij. So instead of modeling rij, if we model zij, we can ensure that interest rate always positive because, as you know, in logarithmic function, the domain is always positive. Then for zij, other thing is same. Other thing is exactly same to Holy model. We have the process such that zi plus 1 j equal zij plus theta I delta plus sigma delta 1/2 and zi plus 1 j plus 1 is zij plus theta I delta minus sigma and root delta, and they have equal probability. So interest rate, log of interest rate can go up or go down with equal chance. Since we fix risk neutral probability as 50%, therefore we have to calibrate. We have to calibrate this one, this theta part. We have to calibrate this one to match our model bond price and market bond price. This part is exactly same to Holy model. In Holy model, we also fix risk neutral probability at 50%. We match theta like that. Exactly same. We fix risk neutral probability and we only match this one. The only difference between Holy model is instead of modeling interest rate directly, we model log of interest rate. Therefore, while zij can be negative, rij is always positive. An example, the strategy to fit the term structure of interest rate is the same as for that of the Holy model. First, we look for theta naught that yields exactly the same price of a bond maturing on k equal 2. Then we move to find theta 1 that fits exactly the price of the bond maturing on k equal 3, and so on. The important detail to notice is the level of sigma that we need to choose for the model. Note that differently from the Holy model, now sigma is the volatility of log interest rate, Zr equal to log of Ri. Therefore, as such, it must be estimated from a log interest rate series. So you download interest rate data, you take log, and you can calculate standard deviation and annualize it. So you download the interest rate data and take log and calculate volatility from that. Taking log differences in monthly interest rate from 1961 December to 2012, we obtain an annualized level of volatility equal to sigma 21.42%. Okay, so we fix sigma and then we match the theta part, similar to Holy model. You can check the link below and then download the spreadsheet and you can do the practice. Let's do it together. So if you click this link, then you can download Excel file as follows. This is the Excel file. So as before, we have data. This is data. This is data for term structure of interest rate. Term structure of interest rate means the shape of this yield curve. And as you know, this and this and this, those three columns all contain exactly same information. Anyway, the interest rate model starts from this one as before, so 1.7%. So in Holy model, we directly model this interest rate. Now in BDT model, Black Dominant Toy model, in this case, we take log and we model log process. So first, we take log ln, log of this one. Right, we have this one. Now, here, as before, we model the process. So let's start from the fresh sheet. So let's call this one as theta naught. We have to use a default name. Let's call this one as BDT 0. Okay, good. Let's call this one as BDT 1. That name doesn't work, so instead of BDT 1, BDT dash 1. Okay. Now here, first, we have to add this one as before. Exactly same to Hoyle model. First, BDT 0 multiplied by delta. Right? Delta was 0.5. Right? Like this one. And then here, now we have to take into account the stochastic part, the risk part. So here we add this one. Let's say this one 4. So here, first minus 4 multiplied by delta to the power of 0.5. This one. This is too long, so reduce decimal point this way. Right? And then this part, interest rate can go down again. So here, well, we can actually, let me start from here. So this one plus BDT 0 multiplied by delta, okay, minus 4 delta 0.5. Well, but instead of BDT1, because we have second one as a Hoyle model, so BDT0 we use BDT1 like this one. And let's reduce decimal point like this. And then we have to fill the other part. So here, okay, here this one is, we can add 2 times of this volatility. So let's copy and paste, copy this one, and then this one is below 1 plus 2 times of this one. And the other thing is the same. And then let's adjust decimal point. Decimal point like this one. Good. Well, this number seems very large negative, not surprising because interest rates are very small. Anyway, now we have low interest rate, therefore we can recover interest rate. We can simply take exponential value, right? So let's make delete it, start again. So let's take exponential of 1, this one, and then copy and paste everything. Right? So we can recover interest rate 3 as before. Other part is exactly same. We can first match bond price maturing 6 months later. So 6 months later, bond price always 100. So let's delete and starting from the beginning. So 6 months later, 1 year later, maturity is 1. So 1 year later, bond price is always 106 months later. We have to discount it with this value multiplied by exponential of minus this rate multiplied by delta. Right? So we have this one and this one. Now here, we can calculate the expected value. Expectation is straightforward because in BDT model, the risk control probability is already 50%. So we add these two, divide by 2, then we have expected value, and we have to discount it back today. So we can multiply exponential of minus 1.74% multiplied by delta, parenthesis, done. So it's a bond price. Now we can compare this and this one. Definitely, our bond price is too low, right? We can match this one, so use the same color. Okay, comparing this one and this one, our bond price is too low. So it means that we have to decrease the level of interest rate in future. So it means that we have to decrease this value. Okay, so first define pricing error, market price of bond minus model price of bond, and square it, and we run optimizer. So data solver, and our target is pricing error. We minimize it, and then change what? We have to change this one. Set a none. Run. Okay, so set an, as we expected, we previously our model bond price was too low, which means that we have to lower future interest rate. In order to lower future interest rate, we have to lower theta naught. And indeed, theta naught is decreased from 1 to 0.72, around 0.72. In this case now, interest rate model about this part and these two, they are all consistent to each other. Now, in order to match the second one, theta 1, now we have to match this one and this one, bond price maturing 1.5 years. Let's highlight this on a different color. Okay, so to review this one, let's review this one. So bond price is all 100 in 1.5 year later. In 100, 1 year later, now the bond becomes a 6 months bond, and that 6 months bond, which is 1 year later, is we discounted with the 6 months rate. So as before, we iterate this process. So exponential and minus interest rate and delta, and then multiply face value. Okay, and then this is 3 are the 1.5 year bond at 1 year later. We have again 3 value because we have 3 scenarios for interest rate. Next, what is the price of 1.5 year bond 6 months later? First, we have to calculate expected value. because of equal chance, expected value just average. Actually, we can change it to average, okay, average, right? And then, but we have to discount it because it's future value, so discount it with this rate multiplied by delta. Okay, and then we copy and paste. And then here, price again, we can calculate average of those two, and then we have to discount it. EXP minus this one multiplied by delta. Done. Now let's compare this one. They are different, so we set a pricing error. This one minus this one, and then squared. We want to make pricing error 0. So we run Excel solver again, and minimize pricing error. And then minimize, and we want to now change it this time. Theta 1. We want to change theta 1 to make pricing error 0. And we'll run solver and done. Okay, so theta 1 is 0.68. Now everything is consistent. Pricing error 0, so 1 year bond price same, 1.5 year price same, and then our interest rate tree like this, and underlying BDT log interest rate looks like this. So we fit it the bond prices for BDT model. Now we have this theta 0 and theta 1. Now we can calculate any derivative prices. So suppose let's make a small exercise. So for example, let's make here. So let's do the call option, put option. How about put option on bond? And let's say put option bond exercise price is, let's say exercise price is let me say 98. Let's say 98.5. Well, that is exercise price. So suppose underlying asset is bond maturing 1.5 year, and exercise price is 98.5. Then suppose we are interested in the price of that option. So put option on bonds maturing 1.5 years later. Okay, so let's say this exercise price as put option K, put K. Okay, so at the terminal price, maturing bond mature 1.5 years, and let's say the maturity of this put option is 1 year. So 1 year later, we have these 3 values. So depending on 3 values, we have 3 values for the put option. So let's write down payoff for the put option. So max put K minus now this bond price and 0. So when bond price is 97.65, payoff is amount around 0.4A, and we can put this down. Well, then when bond price is 98.26, our put option payoff is 0.23. And when bond price is 28.7, this is greater than 98.5. So because it's put option is right to sell, therefore put option payoff is 0. People don't want to sell a bond whose price is 98.7 at 98.5. They don't want to sell their asset at low price. So option is not exercised. So anyway, we calculated value of the put option or payoff of the put option at the terminal at the expiration of the put option. So let's highlight this one. Highlight this one. And then now, here, we want to calculate what is that put option price in 6 months later. Now we know risk neutral probability is always 50%. So first we get the average of these two. So it is a future value, future expected value of the put option on bond. So because it is a future value, so we have to discount it back. And then because the interest rate is at this point this one, so we have exponential of minus 2.90% multiplied by delta for 6 months. Yeah, done and done. So depending on the interest rate, put option price on bond maturing 1.5 years is like this one, and now current price is therefore, again, we can calculate average. And then we now discount it, this rate multiplied by delta. So we are done. So this is our final value. So we just calculated value of the put option. The maturity of the put option is 1 year, and the put option is written on a bond. And the bond is zero coupon bond, and the maturity of bond is 1.5 years. We are done. So students shouldn't be confused. There are two maturities, one maturity for bond and another maturity for option. So this is the price of the put option process. Now, simple BDT model, this is a larger tree. So if we have more data on yield curve or term structure of interest rate, then we can calibrate all those setas in the BDT model. Once we calibrate those setas, then we can build this tree, right? These two numbers are what we already have, right? So they are all written in percent. They are multiplied by 100. So with further data, we can calculate those things.